Good morning, my dear students. In the last class, we have discussed regarding the accelerators. What is the accelerator? What are the different types of the accelerators? All those in detail we have discussed in the last lecture. Today, we are going to discuss regarding the detectors. Isn't it? Now, what are the detectors means? The detectors are the devices which are used in order to find how many number of the particles emitted in a given time from a radioactive material. Those devices are named as the detectors. Once again, that is, detectors are the devices which are used in order to determine how many number of particles are emitted in a given time by a radioactive material, isn't it? And here, let us try to understand then how can we find the number of particles emitted in a given time emitted by a radioactive material. Now, the first detector we are going to discuss is about the scintillation detector. Now, before going to discuss in detail regarding this, what it is the scintillation detector, then what are the important points we'll come across during the discussion of this one. Let us try to understand those points so that the remaining will become easy for you. Now here, I think in the previous classes you have studied the three important points regarding the photoelectric effect, Compton effect, and pair production. Now let us try to understand. No doubt. Then regarding all these three, that is photoelectric effect, Compton effect, and pair production, then you have studied in your lower classes, but you might have forgotten. Just to recall those points once again. Now, first is what is the photoelectric effect? The photoelectric effect, it is the phenomena of emission of electron from a metal surface under the influence of radiation of suitable frequency is known as the photoelectric effect. That is, its meaning is that. Now, let us consider this is a metallic surface. The emission of electron from this metal surface during or under the influence of electromagnetic radiation of suitable frequency is known as the photoelectric effect. Its meaning is that when the radiation of suitable frequency, that means it shows that if any radiation is incident on it, then it will not emit the electrons. When a radiation of suitable frequency is incident on it, then only it emits the electrons. Then this, the phenomena, it is known as the photoelectric effect. Now see, in the lower classes you have studied that why, that is, in order to emit the electron from a metal surface, why you need a radiation of suitable frequency, isn't it? That all those points you have studied in your lower classes. Once again, I don't want to go in detail about this one. If you want the information, then you go through the books which are already you have studied in your lower classes, but it is the most important one. Now, this is the photoelectric effect. The next is, the second one is the Compton effect. I think regarding this Compton effect in 5th semester, you might have studied, isn't it? Then what is that one means? Here, when a photon of certain energy is the incident on any metal surface, it was found that the wavelength of the reflected light or deviated light or scattered light, it is greater than the wavelength of the incident. That is, if this is the lambda is the wavelength of incident light and lambda dash is the wavelength of the scattered light, then it is observed that lambda dash, it is greater than lambda. Then this is known as the Compton effect. What it is? When the radiation of wavelength is incident on any surface, it was found that the wavelength of the scattered light, it is greater than the wavelength of the incident. This, the phenomena or this effect, it is known as the Compton effect. Now the question is that I want to make it clear for you this point. then wavelength of the scattered light is more than the wavelength of incident. Means now energy of a photon, general formula is what? E is equal to h nu, isn't it? Now if you express this one in terms of wavelength, what you get? E h as it is, you write, then the frequency is nothing but c by lambda. Then here energy, it is directly proportional to frequency and inversely proportional to the wavelength, isn't it? Because here the wavelength, frequency and wavelength are inversely proportional, so that energy, it is directly proportional to the frequency and energy is inversely proportional to the wavelength. Means here the wavelength is more than, wavelength of scattered light is more than the wavelength of incident light. Means then here if you consider the energy of this, it is equal to E, and energy of this is what it is, the E dash, isn't it? Then it shows that E dash is less than E, isn't it? That means energy of the scattered light is less than the energy of the incident light, isn't it? Then what happens to that difference? What it is the amount of energy, isn't it? Or delta E, it is equal to what you get it here, E minus of E dash, isn't it? Now because E dash is less than E, means then delta E is equal to E minus of E dash. Then what happens to this one? Now this, what it is the difference of energy, it is used for the removal of the electron from this surface. What will happen? Then whatever the difference of energy is there, then that difference of energy, it is used for what it is the removal of the electron from this metal surface, for, or means in ionizing this, what it is this material. That means it shows that even in Compton effect also, when the radiation is incident on any surface, then what it is this in this case also the electron is what it is released, isn't it? Now see, this is the Compton effect, and the next is another is what it is the pair production, isn't it? The third, it is what it is the pair production. Pair production. Yes. Then what is the pair production? Means when a photon of energy, this is a photon of energy E is equal to 1.02 million electron volts or greater than 1.02 million electron volts, then this photon, it splits into a pair of electron and a positron, this one. Then this is known as what it is a pair production. That is, when a photon of energy is it greater than or equal to 1.02 million electron volts, then this photon, it splits into electron and a positron pair, then this is known as what it is a pair production. The condition is that then which photon will split into electron and positron? The condition is the energy of the photon should be greater than or equal to 1.02 million electron volts. Minimum energy is 1.02 million electron volts, and it may be more than also. But if the energy is less than, what it is the energy of a photon less than 1.02 million electron volts, then such a photon will not undergoes into the pair production. Why it is means I don't want to go in detail about this one. Then regarding this also already you have studied in your lower classes, isn't it? Now see, this is what the photoelectric effect, Compton effect, another is the what it is the pair production. Once again I repeat here, what is the photoelectric effect means? It is the phenomena of emission of electron from a metal surface when the radiation of suitable frequency incident on it. This is known as the photoelectric effect. What is the Compton effect? When what it is the phenomena of the, or in another way, very simple way, is that when any radiation is incident on a metal surface, then it was found that the wavelength of the scattered light, it is greater than the wavelength of the incident light. Then this is known as what it is the Compton effect. Then here, if the wavelength of the scattered light is more than the wavelength of the incident, means energy of the scattered light is less than the energy of the incident light. Then what happens to that difference amount of energy? That difference of amount of energy, it is used in the releasing the electron from the metal surface. Isn't it? What is the pair production? That is, when a photon of energy greater than or equal to 1.02 million electron volts, that photon, it splits into electron and positron pair. This is known as the pair production. Then the thing is that either it may be photoelectric effect, it may be Compton effect, or it may be what it is the pair production. Whatever the energy of the radiation is there, isn't it? That energy of the radiation, some energy of the radiation, it is used in the removal of the electron. In photoelectric effect, electron is released. In Compton effect, electron is released. And in pair production also, the electron is released. In all these three effects, isn't it, the electrons are released, isn't it? Now, these are the three important what it is the effects. That is the photoelectric effect, Compton effect, and what it is the pair production. Now, these are the three important effects. Now, see, after understanding this one, isn't it, let us come to what it is the one more point that before going to discuss regarding this what a scintillation counter, one more point, whatever it is useful for you, that I want to make it clear. Now, see, for our understanding, isn't it, for our understanding, let us consider this is a metal surface, isn't it? This is a metal surface. When the radiation of a suitable frequency incident on it, according to the photoelectric effect, it emits the electrons, isn't it? It emits the electrons. Then here, in the photoelectric effect, you might have observed that the what it is for the removal of the electron, a definite amount of energy it is required to release the electron from the metal surface. Then that much amount of energy, or the minimum energy required to release the electron from the metal surface, isn't it? That what it is the energy, it is known as what it is the work function. It is known as the work function. Then here, for example, let us consider work function, it is equal to 2 joules. How much it is? 2 joules. Then here, then this is a photon of energy, it is equal to 5 joules. Isn't it? This is a photon of energy equal to how much it is? 5 joules. When this photon incident on this, it releases the electron, then the minimum energy required to remove the electron from the metal surface, that is called as the work function, that is equal to 2 joules. Now, when a photon of energy 5 joules strikes to this material, then out of 5 joules, 2 joules is used for the removal of the electron. That is called as the work function. And whatever the remaining energy is there, remaining energy means what? After supplying this much amount of energy, how much amount of energy remains with this one? How much it is? 3 joules. Then that 3 joules of energy appears as the kinetic energy of the emitted electron, isn't it? Then here, so that this energy, it is of a photon, it is equal to work function plus kinetic energy. Work function plus kinetic energy. Now, work function is 2 joules and the remaining energy, it is kinetic energy. Therefore, this kinetic energy, it is equal to how much it will happen? 5 minus 2, that is equal to 3 joules. It will appear as the kinetic energy of the emitted electron. Then this is the equation, we call it as what it is the Einstein's photoelectric equation, isn't it? Now see, with the help of what it is these points, now let us what it is try to understand about this what it is the scintillation, what it is the detector. Now first let us try to understand the what it is the construction of this scintillation detector. Now here this what it is it use the construction of the scintillation detector. Now this is a photocathode, isn't it? And these are the electrodes, they are known as what it is the diodes. Now what are the diodes means? The surfaces of these diodes are coated with such a material that when one electron strikes on this surface of this diode, it releases more number of electrons. That is, the surfaces of the diodes are made such that when one electron strikes on it, it releases the more number of what it is the electron. For our understanding, let us consider if one electron strikes to it, then for one electron, let's say it produces 10. That is the example I am saying. If two electrons incident on it, then for one electron it is 10, means for two electrons means 20. Like this, isn't it? Then those electrodes, they are known as what it is the diodes, isn't it? Now this is a what it is the anode. Now this complete what it is a tube, it is known as what it is the photo multiplier tube, isn't it? Now see, after understanding what is the construction of this scintillation counter, now let us try to what it is the understand about the theory of this scintillation counter. Now from here onwards, you must be very careful. Then word by word carefully you listen here. Now there are certain organic and inorganic materials are there such that when the light is incident on it, it produces the scintillations, isn't it? That is, it produces the flashes of what it is the light. Then those flashes are known as the scintillations. Hence, this what it is the detector, it is named as the scintillation detector, isn't it? That is, there are certain what it is the organic and inorganic materials are there. When the light is incident on it, then it produces what it is the flashes of light. Those flashes are named as the scintillations. Hence, this detector, it is named as the scintillation detector. Now, let us what it is the try to understand here how this counter detects the what it is the number of particles emitted in a given time by a radioactive material. Let us try to understand here. Now here, this is a what is the source of the radioactive material. Source of radioactive material means it emits alpha, beta and gamma, etc. Now, when any particle incidents on this what it is a material. Now here there is a organic or inorganic material, it is there. Then already I have made it clear that then there are certain organic and inorganic materials are there. When any charged particle or the light is incident on it, isn't it? That produces the flashes of light, and those flashes they are named as what it is a scintillations, isn't it? Now what will happen is, now let us consider this is a source of a radioactive material. It emits either alpha, beta or gamma. Now that what it is the particle which is emitted, it enters into this material. When it enters into the material, whatever the energy of the particle is there, then it loses its energy. In the what it is a form of the photoelectric effect, Compton effect, or what it is a pair production. Its meaning is that whatever the particle it is what it is emitted from the source, that particle first strikes that what it is the organic or inorganic material. When it strikes that material, then what will happen is whatever the energy of the particle which is incident here, then that particle it loses its complete energy. Either in the form of photoelectric effect, or in the form of the Compton effect, or in the form of the pair production, isn't it? Then in any of these three effects, it loses its complete energy. Then already we have discussed that either it may be the photoelectric effect or Compton effect or pair production will takes place. Ultimately, it releases the electron. Then whatever the electron it is emitted either by photoelectric effect or Compton effect or pair production, then that emitted electron, it strikes the other atoms of the material, as a result of which those atoms goes to the excited state. Are you following? That means whatever the electron it is emitted either by photoelectric effect or Compton effect or pair production, then the energy of that electron, is it, or when that electron strikes the other atoms of this scintillation material, then those atoms goes to the excited state. And already you have studied that if any atom goes to the excited state, it cannot stay a long time in the excited state. Immediately it de-excites, isn't it? And during the de-excitation, it emits the energy in the form of the light, isn't it? And that light, it appears as a flashes of light. Those are known as the scintillations, isn't it? Now, whatever the light is emitted during the de-excitation of the atoms, that light strikes to this photocathode, isn't it? Whatever the light is emitted, that light strikes this, what it is, a photocathode. When the light energy strikes the photocathode, due to the photoelectric effect, this photocathode, what will happen? It emits the electron due to the photoelectric effect, isn't it? Now, whatever the electrons are released from this, what it is, a photocathode, and here we are applying a certain potential difference, isn't it? When you apply certain potential difference to any charged particle, electron is a charged particle, negatively charged particle. When it is subjected to certain potential difference, then it gets accelerated. Accelerated means what? It gains the energy, isn't it? Then as it gains the energy, that means its speed increases and it moves towards this, what it is, the dynode. Now, whatever the electron it is coming from here, strikes to this dynode, then already I made it clear that the surfaces of the dynodes are made such that if one electron strikes on it, then it releases the more number of electrons. I had given the example that suppose let us consider, for our understanding it is, if one electron strikes on this surface, it releases the 10 electrons. If 2 electrons incident, then 20, like this it is. Now, whatever the electrons are released from this, a photocathode, those electrons are accelerated by the applied potential difference, isn't it? Then as a result of which, they gains the energy and they move forward, isn't it? And when those electrons strike to this, dynode surfaces, then the more number of electrons are released. Now let us consider, for our understanding it is, if let us say one electron strikes on it, when one electron strikes on it, it releases the 10 electrons, isn't it? Then again, here there is again potential difference is applied. Then here there is some resistance is there, means what? Then it is giving, or it is providing a definite potential, the electric potential. Then those, electrons, which are emitted from this first dynode, then those electrons are again accelerated under this potential difference. And they move forward and they strikes to the second dynode. Then yes, we have taken an example that if one electron strikes to first dynode, then for one electron, it provides or it emits the 10 electrons. Those 10 electrons again gets accelerated, move forward and strikes to the second dynode, isn't it? That means all those 10 electrons reaches to the second dynode. Then for one electron, 10 means, for 10 electrons means 100 number of electrons you get here. Again, those 100 number of electrons are accelerated by this potential difference. Then those, 100 electrons reaches to this third dynode. Then how many you will get? Then 10 times it is multiplied. Is it right now? Isn't it? For one, it is giving 10. Isn't it? 10 times. Then from here it is a 10. Next here, multiply by 10, 100 you get. Next again multiply 1000 you get. Then like this, isn't it? When you put the number of dynodes in series, then the number of, more and more number of electrons are produced. And when those, electrons comes near the anode is kept at high positive potential. isn't it? Then those electrons are what it is attracted or reaches to this what it is positively what it is the anode. Then they what it is flows in this what it is the circuit, and here there is a capacitor where it is what it is stored, and it provides a particular voltage that in the form of the pulse. Then it is having what it is a certain potential, means it is having a definite amount of what it is the energy. Then that energy, it is nothing but, as you know, that E is equal to Q into what it is the V, isn't it? Then here Q is the charge and V is what it is the applied potential. Then here how much amount of charge it is reached to the anode, isn't it? That if 1 electron it is reaches here, then charge is equal to charge due to 1 electron. If 10 electrons reaches here, then it is charge due to the what it is the 10 electrons, like that. If 1000 number of electrons reaches here, then charge is equal to charge due to the 1000 number of electrons. That then how much what it is the voltage or potential difference you applied it, then that gives it is what it is the amount of energy it is reaching here. Then what will happen is that energy will appear in the form of the pulses, isn't it? Then here you are observing that the amount of energy, isn't it? Ultimately, the amount of energy you are getting finally, that energy, it is directly proportional to the charge. Why? Means the potential difference, applied potential difference, it is a constant, isn't it? How much of what it is the potential difference you have applied here, that is a constant, but this energy, it is directly proportional to the charge Q, isn't it? If what it is the more number of what electrons reaches to the anode, then the charge will be more, ultimately energy is more. If the less number of electrons what reaches to the anode, charge is less, energy is also be less. Then here what will happen is final energy, whatever it is reached here, then as I had told you that this energy will appear in the form of a pulse. That means in the while you are doing the experiment on CRO, you might have observed that the waves you will get like this one. These are the pulses. Sometimes you will get this type. Then these are all the pulses, and this is a pulse height. Then this pulse height, it measures what it is the energy of the wave, etc. Then if the pulse height is more, then ultimately that wave is having what it is of more energy. If the pulse height is less, then its energy is also be what it is the less. Then here whatever this total energy you get, then that energy, it is proportional to the pulse height. That means if the pulse height is more, means the energy is what more. If the pulse height is less, then energy is also be less. Now this, that is either the pulse height or total energy, it depends upon the which factor, means it depends upon the energy of the incident particle to the material, isn't it? If the energy of the incident particle is more, then pulse height is more, energy is more. If the energy of the incident particle is less, then pulse height is less, energy is also be less. That means the pulse height, it is directly proportional to the energy of the incident particle. Then how it is, means, then let us try to understand in this way. Now if the energy of the particle is, that is whatever the particle it is incidenting on this, what it is the material, that is the organic or inorganic material, if the energy of the particle is more, then it, what it is provides the more number of electrons are released from the photocathode. If the energy of the incident particle is more, then more number of electrons are released from the photocathode. If the more number of electrons are reached from the photocathode, then the number of electrons reaching to the anode are also be more, isn't it? If more number of electrons reaches here, then this charge is more, means energy is more. That is the pulse height. So that we say this pulse height is ultimately proportional to the energy of the incident particle. Now let us take an example. We are having the 3 diodes. If one particle it is, or if that particle releases one electron from this photocathode, then what will happen? For one electron here, next it is what it is a 10, next it is what it is a 1000. Then ultimately 1000 number of particles are reaching to the anode. When it is, if one electron it is released, what emitted from this photocathode. Next, suppose if the 2 electrons are released from this photocathode, then here you will get 20, then here you will get multiply by 10, that is what is the 200. Now here you get 2000, isn't it? That means if one electron released here, then here you are getting 1000. If 2 electrons are released here, then you are getting the 2000. Are you followed? That means here the number of electrons reaching to the anode, it is proportional to the number of electrons released from the photocathode. Then whatever the number of electrons released from the photocathode, it depends upon the energy of the incident particle, isn't it? If the energy of the incident particle is more, then more number of electrons are emitted from the photocathode. As a result, the more number of electrons reaches to the anode, hence the energy is more and pulse height is more. Then if the energy of the incident particle is less, then less number of electrons are released from the photocathode, then less number of electrons reaches to the anode, then pulse height is less, then energy is also be less. Therefore, this shows that the energy of the incident particle is directly proportional to what is the pulse height, isn't it? That means if you know the pulse height, then you can calculate what is the energy of the incident particle. Hence, then this what it is a counter, it is used for the measurement of the energy of the incident particle also, isn't it? That is, this detector, it is used for the measurement of the energy of the incident particle also. How means? Then here, first what we do is, then this what is the counter, it is what it is the calibrated, isn't it? Calibration means what? I want to make it clear in a simple way that calibration means what you have to do is, first you send the particle of known energy. First you send the particle of known energy, then you find or you measure the pulse height, isn't it? What you have to do? You send the particle of known energy, then you find its corresponding pulse height. By knowing that, you can find the unknown energy also. How means? Let us take an example. Energy of the incident particle which is known. Let us say energy, it is equal to 10 million electron volts, isn't it? Now, for energy E is equal to 10 million electron volts, then pulse height, it is equal to 10 centimeter, let us say 10 centimeter. That means this pulse height of 10 centimeter for the energy of how much it is, 10 million electron volts. That means for 1 million electron volt, how much you get? For 1 million electron volt, pulse height is equal to what it is, the 1 centimeter. Isn't it? This is calibration, isn't it? That means if you are getting the pulse height is equal to 1 centimeter, means it is understood that the energy of the incident particle is equal to 1 million electron volt, isn't it? If the pulse height is 2 centimeters, then it shows that energy of the incident particle is what it is, 2 million electron volts. Now this is what it is, the calibration. Now what you do is, how will you find the energy of the incident particle? Now let us consider the particle which is entered here. We don't know its energy, isn't it? Send the particle whose energy is to be determined. That is, pass the particle whose energy has to be determined. Then you find the pulse height, isn't it? Now let us consider the pulse height. It is equal to 3.5 centimeter. Then energy is equal to how much? For 1 centimeter, already we have calibrated that for 1 centimeter height, energy is equal to 1 million electron volt. Then for a pulse height of 3.5 centimeters, then energy is equal to 3.5 million electron volts, isn't it? Suppose if you get pulse height is equal to 5 centimeters, then it shows that energy of the particle is equal to 5 million what it is, electron volts. In this way, isn't it, we can determine, isn't it, we can determine what is the energy of the incident particle, isn't it? Now the next is here, how to determine the number of particles emitted in a given time. The number of particles emitted in a given time. Now what you do is here, then in a given time, how many number of pulses you get? You measure it. Isn't it? Then each pulse corresponding to one particle. Isn't it? If 2 pulses you got means it is the 2 particles. 3 pulses means 3 particles. Like that. The number of pulses is equal to the number of the particles entered here. Isn't it? Then what you do is you measure the number of pulses in a given interval of time. Then those many number of pulses, it corresponds to the number of particles entered in a given time. In this way, we can determine how many number of particles the source is emitting in a given time. We can determine it. At the same time, what is the energy of the particle emitted, that can also be determined by using this, a counter. Are you followed? Therefore, this is the way how we can, used for the measurement of the number of particles emitted from a radioactive source in a given interval of time. In addition to this one, we can calculate the energy of the emitted particles also by using this, a scintillation counter. Therefore, this is the way how this scintillation counter, it is used for the, determination of the number of particles emitted in a given time and the energy of the particles, isn't it? Now see, with this, then we will conclude this, a scintillation counter. In the next class, we will discuss about one more, a counter, that is the GM counter. I think for understanding the GM counter, it may not, make any difficulty for you, because already you have done the experiment in the 5th semester by using this GM counter. You can understand very easily. Then in the next lecture, we will discuss then what is the construction, principle and working of the GM counter in the next class. Now, thank you one and all. I will stop here.